In this video by the Aggie Math Learning Center, we'll be covering how to solve problems using exponential and logarithmic models. We will work through 3 word problems and discuss the different methods to solve them. Problem number 1. The city, Salisbury, has 3,000 rabbits in 1924. Their population grows exponentially. In 1926, there are 10,000 rabbits. How many rabbits are there in 1928? Take a few minutes to try this problem. The first thing to remember is that this is dealing with exponential growth. So we want to be using the equation p equals p naught times e to the k times t. Now let's identify the information given in the problem. Our starting population is 3,000, so p naught equals 3,000. After 2 years, our population is at 10,000, so we can use t equals 2 and p equals 10,000. Therefore, the only thing we don't know is k. We can solve for that first and then figure out how many rabbits there are after 4 years. With the information we have, our equation is 10,000 equals 3,000 times e to the 2k. We'll solve for k by rearranging our equation. First, we'll divide 3,000 from both sides to give us 10 divided by 3 equals e to the 2k. We can then take the natural log of both sides to get k out of the exponent. This will leave us with the natural log of 10 over 3 equals 2k. We then divide by 2 to get an expression that we can put into our calculator. This gives us k equals 0.60199. Now that we know k, we have everything we need to find the rabbit population after 4 years. We will plug in our values for k, t, and p naught into our equation and solve for the population p. This gives us p equals 3,000 times e to the 0.60199 times 4. After plugging this into our calculator, we get the population to be 33,333 after 4 years. So our solution is 33,333 rabbits. Problem number 2. A radioactive isotope experiences exponential decay. 50 grams of this isotope is taken for studying. After 20 hours, only 5 grams remain. What is the half-life of this isotope? Pause the video and give this problem an attempt. In this problem, notice that we are using an exponential decay model. Therefore, we want to be working with the following equation. A equals a naught times e to the negative kt. From the word problem, we know that the starting amount, a naught, is 50 grams. We also know that after a time t of 20 hours, we have the amount a of 5 grams. We can plug these values in and solve for k. After plugging these values into the equation, we get 5 equals 50 times e to the negative 20k. To solve for k, we'll divide both sides by 50 to get 0.1 equals e to the negative 20k. We then take the natural log of both sides to get the natural log of 0.1 equals negative 20k. We then divide both sides by negative 20. After plugging that into a calculator, we see that k equals 0.11513. Now that we have k, we can use it to find the time at the half-life. Half-life means that only half of the starting amount is left. So we know that a equals 25. We'll plug in our values for a naught, and k into our equation and solve for t. Once plugged in, our equation looks like 25 equals 50 times e to the negative 0.11513 times t. We'll divide both sides by 50 to get 0.5 equals e to the negative 0.11513 times t. We will then take the natural log of both sides to give us the natural log of 0.5 equals negative 0.11513 times t. We'll then divide both sides by negative 0.11513 to give us t equals 6.021. Therefore, our half-life of this isotope is 6.021 hours. The third problem we will work with is a logarithmic model problem. 2 earthquakes happen in Seattle, one the aftershock of the other. The magnitude of the first earthquake was 8.3, followed by the aftershock of magnitude 6.4. What is the ratio of the intensities of the first earthquake to the second? Take a moment to think through this problem on your own. The first step is to realize that we have an equation for this type of model that relates two earthquakes' magnitudes to their intensities. We know this equation to be m sub 1 minus m sub 2 equals log of I sub 1 divided by I sub 2. We know that the first earthquake has a magnitude of 8.3, so we know m sub 1 equals 8.3. We also know that the aftershock has a magnitude of 6.4, so m sub 2 equals 6.4. Therefore, we can set up our equation like 8.3 minus 6.4 equals log of I sub 1 divided by I sub 2. We are looking for the ratio of the intensities, so all we need to do is isolate I sub 1 divided by I sub 2. First, we need to subtract 6.4 from 8.3 to get us 1.9. We can then do the inverse operation of log base 10 to remove the log from the function, which will leave us with 10 to the 1.9 equals I sub 1 divided by I sub 2. 10 to the 1.9 is equivalent to 79.43, so we can say that the ratio of the earthquake's intensities is 79.43. If these or any other concepts require some more of your attention, feel free to watch this video again, reach out to your professor or recitation leader, or utilize the free tutoring services offered at the Aggie Math Learning Center. We hope this video has been helpful.